So our final section in Chapter 4, Section 7, we're going to learn how to write exponential and power functions. Some of this is going to be relatively complex, so please take good notes and pay close attention. We want to talk about power functions and exponential functions, and really the name of the function relates to where the variable is. So if y is equal to a times x to the b power is a power function, because x is the base of a power, and y is equal to a times b to the x power is an exponential function because x has become an exponent. So these are the two different functions we'll be working with in this section. So if we go through the process of writing an exponential function, so again, remember the form that we're working on is a times b to the x power. I don't know a and b, but I do have a couple of pairs here of x's and y's. So what we're going to rely on is back what we learned in Algebra 1, which is the concept of substitution combination. So anytime I have two variables that are missing, if I can write two equations, it'll help me find the two variables. So when y was 3, when x was 1, and then y was 12 when x was 2. So if I go ahead and take this first equation and I solve it for a, I'm going to get 3 divided by b is equal to a. And then I'm going to take this and I'm going to substitute it into my other function in place of a. So I'm going to have 12 is equal to 3 divided by b times b squared. And by doing substitution, I've gone from having equations that have two variables to an equation that has a single variable. This will now allow me to solve for b. So b squared times 3 over b is going to end up being just 3b. And when I divide by 3, b is equal to 4. If I take this value of b and I plug it back up into the original equation, 3 would be equal to a times b to the first power, and b to the first power would be 4. Now I can solve a is equal to 3 divided by 4. So my equation now is y is equal to a, which is 3/4, times b, which is 4, to the x power. Okay, so let's go ahead and do that one more time. So I know that y was 24 when x was 2, and then y was 144 when x was 3. So I'm going to go ahead and solve for a again. So a would be equal to 24 divided by b squared. I'm going to plug that in here in place of a. 144 would be equal to 24 divided by b squared times b cubed. This is going to simplify to be 24b is equal to 144. So b would be equal to 144 divided by 24. Which is 6. So 6 is equal to b. If I plug the 6 back up here, so I'll have 24 is equal to a times 6 squared. 6 squared is 36, so 24 divided by 36 would be equal to a, and that's going to simplify to be 2/3. So when I write my equation, y would be equal to 2/3 times b, which is 6, to the x power. Okay, so write two equations. Solve one of the equations for a. You should use the one with the b to the least power, with the lowest power value of x. Then, once you've got that, plug it into the other equation in place of a. which is what we did here. Simplify and you get b. Plug back into one of the original equations and you find a. Okay, so go ahead and practice doing that. Do problems 5 and 6, and then come back when you're done. So now we're going to do something that's a little trickier. I'm given a rule here that says that if I have a data set and I don't know if it fits an exponential model, because in life we don't really know sometimes. We get data and you look at the input-output table, maybe this is monthly sales, maybe this is homelessness, this might be figures for anything based on years and data. For instance, if we're studying homelessness, the millions of homeless people in years since 2005, this could be that data. If we want to try to figure out what model it fits, we can test for an exponential model by taking a look at a new data set that includes the x value we had originally plus the natural log of the y value. And if that creates a line, then we know we have an exponential model and we can proceed. So if we go ahead and then recreate the table, so we'll have x times the natural log of y. So my x values are 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. And then I'm going to take these interesting values of y and I'm going to plug them into my calculator to get the natural log of those numbers. So when I plug them into my calculator and get the natural log of 3.3, that's 1.19. The natural log of 10.1 is 2.31. The natural log of 30.6 is 3.42. The natural log of 92.7 is 4.53. And the natural log of 280.9 is 5.64. So now I've done some rounding here, and that's going to introduce rounding error, right? So all of these were very long decimals that I've rounded down to 2% or 2 decimal places. So remember that anytime you're doing rounding, it's going to introduce something that is going to be introduce some level of error. So if I start to graph this, 1.19, at 2 we're at 2.31, about there. At 3 we're at 3.42. At 4 we're at 4.53. So you can see we're pretty much finding a linear model here. Okay, so now that I'm looking at the linear model, if I say, okay, I now want to write the exponential model that makes this original data set. So if we go through, now that this is linear, right? So this we've identified as an exponential model, but this is a linear model. I'm going to start by writing the linear equation. So I know that I'm going to use my y minus y1 is equal to the slope times x minus x1 that we learned in Algebra 1. And I'm going to go ahead and I'm going to write the equation of the second function, the linear function. So I can pick I need to pick 2 points and find the slope. So I'm going to go ahead and take this point and make it my first point. And I'm going to take this point and make it my second point. So my slope will be equal to 2.31 minus 1.19, all divided by 2 minus 1. So 2.31 minus 1.19. It's going to be over 1. So I have a 2, 1, 1.12 over 1, which is 1.12. So that's my slope, 1.12. I can pick either of these points now for y1 and x1. I'm going to go ahead and use the first one. So I'll have y minus 1.19. Then over here I'll have x minus 1. If I go ahead and start to simplify this, I'll have y minus 1.19 is equal to 1.12x minus 1.12. And actually this is natural log of y, not y. So natural log of y will be equal to 1.12x. If I add 1.19, there's a difference of 0.07. Now if I want to solve for y, this is where, so far I've been working with this as a linear function, but now I can turn it back into an exponential function. If I want to get rid of the natural log part of this, I'm going to exponentiate either side on a base of e. Right? And if I simplify this, then y will be equal to, let's go ahead and start to break some of this apart using the properties of exponents. All right, so if I have, this would be e to the 1.12x times e to the 0.07. Okay, because when I multiply with the same base, I add the exponents, so I can break that apart. And equally, I could say this is e to the 1.12 to the x power, because when I take a power to a power, I multiply the exponents. And now I'm going to start simplifying these e's to powers. So let's say this is e to the 0.07. I'm putting it into the exponential model. If I take my calculator out, and I go ahead and do e to the 0.07 power, that's 1.073, or I'm just going to say 1.07 to make this simpler. So this becomes 1.07, y is equal to, times, and now let's find what e to the 1.12 power is. E to the 1.12 power, probably going to be about, there we go, 3.06. So that goes in here, 3.06 to the x power. So what I've done is, based on an input-output table or a graph, I can check to see, is this an exponential model? And we did that by taking the natural log of the outputs and plotting them to see if they became linear. They did. Then we went ahead, and because this was linear, we treated this as a linear equation because that's what it is. We wrote the equation of the linear equation. We completed that down here. And then by exponentiating either side, I turn it back into the exponential model. So go ahead and practice a problem like this. I know these are difficult. I'm only asking you to do one. So go ahead and give this a try, right? Convert the outputs into the natural log of the outputs, graph and see if it's linear, and then treat it like a linear function to write the linear equation, and then exponentiate to turn it back. Okay, so now if we want to write a power function, right? Power function is in this form, y is equal to a times x to the b power. I know that y was 9 when x was 5. Y was 9 when x was 5. And I know that y was 34 when x was 8. Right, and the same ideas, I'm going to go ahead and I'm going to solve for a, and I'm going to substitute. So a would be 9 over 5 to the b power. And when I substitute that into the other function in place of a, 9 over 5 to the b power, that times 8 to the b power. Okay, so now when I am multiplying a fraction times an integer, I can start moving some of these things around a little bit. I can take 9 over here and make this 8 to the b over 5 to the b. This is still the same, right? Equals 34. I can divide 34 by 9. And this can become 8/5 to the b power. Right? Now, if I go ahead and work through this, I'm going to get a fraction and another fraction. So let's go ahead and find out what those are. So 34 divided by 9, 3.7, essentially repeating. So let's go 3.77 is equal to 8 divided by 5, 8 divided by 5, 1.6. 1.6 to the b power. So if I want to find b, I'm going to take a log base 1.6 of either side of this function. And I'll get that b, because this cancels that, b will be equal to, I'm sorry, log base 1.6 of 3.77. I didn't write that down. My mistake. So let me go ahead and clean this up. Log base 1.6 of 3.77. So if I use the change of base formula, then I will take the log of 3.77 divided by the log of 1.6, and I get 2.82. So b is going to be equal to 2.82. Now if I go ahead and plug back up into one of these guys, 9 is equal to a times 5 to the 2.82 power. Then I can find what 5 to the 2.82 power is. 5 to the 2.82 power. Yeah, 93.56. So I'll get 9 is equal to a times 93.56. So a will be equal to 9 divided by 93.56. It's basically going to be 1/10. So 9 divided by 93.56 is 0.096. So if a is equal to 0.096, now I know a and b. I can write my function y is equal to a, 0.096, times x to the 2.82 power. Okay, so a little long and a little tedious. I'm not going to make you go through watching that a second time, doing a second example. I think that was probably enough. So go ahead and practice that. Do problems 19 and 20. You'll get a little shot at it. And then we're going to look at doing the same thing that we did before with power functions. So when we want to write a power model based on having basically an input-output table or a series of points, I'm going to go ahead and use this idea up here, that if the set of transform points fits a linear pattern, so now I'm going to take the natural log of each item, and I'm going to create a new table, and I'm going to plot that new table. So what I've done is I've gone ahead and I've taken the natural logs of each of the ordered pairs and I've written them into a table. And now what I'm going to do is I'm going to go ahead and I'm going to graph this. So to check to see if it's linear. So I'm going to copy this table and I'm going to put in a blank page here. Here's my table. All right, and then we're going to go ahead and we're going to plot this and see whether or not it fits a linear pattern. Okay, so at 0, I'd be at 0.405, right about there. At 1, at 0.693, that's a little bit in here, right? A little more than half. I'm at a little more than 1.5, so right about there. Then at 1.099, so a little tiny bit more than 1, I'm at 2.25, so 2 1/4, 1, 2 1/4. And you can see it looks like it's shaping up to be linear. So at 1.3, a little less than 1.5, I'm going to be at 2.734, so that's right about up here. And at 1.609, I'd be at 301. It looks like we're pretty much following a linear pattern. So what that means then is I'm going to go ahead and take this now, and I'm going to work with this as though it were a linear pattern. So I'm going to pick a couple of points, and in this case, the points that I'm going to pick, and it doesn't matter which points you pick, right? I'm going to pick this point, and I'm going to make that point 1, and then I'm going to pick and I'm going to pick this point, and we're going to make it point 2. Okay? But I could pick any of the 2 points and go ahead and do this, and I would get the same result. So when I go through and I'm going to work with this, first thing I want to do is I want to calculate the slope. So I'm going to find the difference in the y values, 3.105 minus 1.569, over the difference in the x values. And I'm going to get 1.536 divided by 0.916, which is equal to 1.677. Right, now I'm going to take my slope and I'm going to do point slope. And the point I'm going to go ahead and use is this last point. I'm going to make this the point for point slope. So I'm going to have the natural log of y minus my y value, 3.105, is equal to my slope, 1.677, times the natural log of x. Remember, we natural logged both things, minus the x value, which would be 1.609. Okay, I'm going to distribute the 1.67, and I'll get 1.677 times the natural log of x minus 2.698. And the natural log of y is equal to, minus 3.105 is equal to that. Then when I add 3.105 to either side, I'll get the natural log of y is equal to 1.677 times the natural log of x plus 0.407. Okay, now again, I want to solve for y, so I'm going to need to exponentiate either side on a base of e. Oops, I'm sorry, I put my plus in the wrong place. Okay, now, what caused my exponents to be added? I'm going to start using, this side is very simple. It simplifies to be y. Great. This cancels that. Move on. What causes my exponents to be added? Well, multiplying items with the same base. So this can be e to the 1.677 times the natural log of x times e to the 0.407. And I'm going to be able to figure out what e to the 0.407 is. So let's go ahead and do that. So I have e to the 0.407, and that's 1.502. I'm just going to call that 1.5. So I'm going to put the 1.5 here. And then this is going to be e. Now I know that when I have this coefficient in front of a log, that could be an exponent on my x, 1.677. So I used the rules that I learned from expanding logarithms to go ahead and make that transformation. Right, the coefficient in front, I condensed it and I made it an exponent on the target of the logarithm. Right, so now this is going to cancel there, and what I end up with is y is equal to 1.5 times x to the 1.677 power. And then we've gone ahead and we've created our power function. Again, long and difficult, right? A little complex. Just be very meticulous in doing the work one step at a time. I only want you to do one of these. Do problem 23, and then come on back and we'll work on another problem. Okay, so in taking a look at this problem, we've got a relationship here between centimeters and weight. So the femur circumference, so the circumference of the femur, a leg bone, in millimeters has a relationship to the weight in the animal. And we want to take a look and see, can we find a relationship and write an equation to predict the circumference of a femur? So the first thing we would want to do is we would want to go ahead and we would want to find out if this fits one of our models. Now, I happen to know that this one fits the power model, and we're going to go through. Remember, we have to do the natural log of each of our values. Okay, and that's going to give me 5.15, 6.57. I did some prep work before launching into the lecture. 4.91, 6.11, 4.54, and 4.96. Now, if you plugged something like this, had a calculator do all of this work, you would get a more accurate answer than I'm going to get. Because I'm rounding, and this is important, I should have mentioned this on the other problems. Because I'm rounding all of my decimals, I'm truncating everything. When you get into these values, when you take something to a power and you've rounded the decimal part of the exponent, it's going to change the answer. You're going to get what's called rounding error. So I have done all this rounding, and the likelihood is I'm going to have problems when I go ahead and work with this in terms of matching the answer in the book. The book assumes you're just going to plug everything into a table and have your calculator do that. I'm not trying to have you do that, because I want to get you to get the sense of what it is that's going on and not just count on technology doing everything for you. Okay, so when I go ahead and create this table, I could go ahead and plot this. Right? So if I pull this guy, sorry, I lost a couple of my values there. And this over here was the natural log of x. If I go ahead and plot these points, 1, 2, 3, 4, 5.15, 1, 2, 3, 4, 5, 6, and a little over, so right about there. So this is 1, 2, 3, 4, 5. This is a little less than 5, and then it's 6.11, 1, 2, 3, 4, 5, 6, a little more than 6. It's about 4.5, and it's right about 5. 2, 3, 4.5. It's a little more than 5. If we go into 2.56, when 2.56, right about there, it's 0.92, so almost -1. And at 1, 2, 3, 0.333 1/3, 1, 2 1/4. So you can see this is largely looks like a linear function when you think of the rounding error, and my inaccuracy of graphing looks like it is. And then if I want to go ahead and go through and do the work, I'm going to start working with those values. Again, I want to take all of this and bring it over here. Right? And I want to pick some values. So now I've determined this is a linear model. I can work with it like a linear function. So I'm going to pick this one. Oops. I'm going to pick this point as one of my points, and then I'm going to pick this as one of my points. Okay, they're pretty extreme. They're the far left and far right. That's going to help smooth out some of my error. So the first thing I want to do is calculate the slope. We've done this before. So I'll have 6.57 minus -0.92. That's plus 0.92. and that's going to be 7.49. And then I'm going to have the difference in my x values, so 5.15 minus 2.56, and that's going to equal 2.59. And then when I divide these two, I'll get 2.89. So that's my slope. Now I'm going to take one of these 2 points, and I'm going to write the natural log of y minus my y value, 6.57, will be equal to my slope, 2.89, times the natural log of x minus 5.15. When we go ahead and distribute the 2.89, I get 2.89 times the natural log of x minus 14.88. And then when I add 6.57 to either side, I'll have natural log of y is equal to 2.89 times, 9 times the natural log of x minus 8.31. And this is my linear equation. Now, to solve for y, I need to exponentiate either side. I'm going to raise each side to be the power on a base of e. I do that because this simplifies to just be y. And remember, if I have subtraction going on here, then there was a certain amount of, right, there was division happening, right, in terms of multiplying my bases. I know that this can also be a coefficient. So this is e to the natural log of x to the 2.89 power times e to the negative 8.31 power. And I think that's going to be a little easier. That when I simplify this, this is going to be equal to 0.00, how many zeros? 0.246 times x to the 2.89 power. So if I move along to try to solve that, I have y is equal to 0.000246 times x to the 2.89 power. 2.89 power. Now if we want to plug this in here, y would be equal to 2.000246 times 68.7 to the 2.89 power. So I'm going to take 68.7 to the 2.89 power, and that gives me 203,612, but then I need to multiply it times 0.000246, and I get 50.1. So y would be equal to 50.1 kilograms. Right? So that's our estimation. Right? Depending on how you round, how many decimal places you round to, this number will change a little bit. So I rounded to only 2 decimal places. If I had rounded to 3 or 4, I probably would have come out with a slightly different answer. Okay? The important thing is you understand the idea that if you convert by taking the natural log of the inputs and the outputs, and it creates a linear model, then you can take those outputs, work with it as a linear equation, and later change it back to being a power function through the properties of logarithms that you've already learned. Okay, a little complex and a little difficult. Don't worry, the testing on this particular portion of things will not be particularly rigorous. So I want you to get a basic general understanding, but no one expects you to become an expert on this today.